In this video we discuss the concept of the internal energy, and then we introduce the first law of thermodynamics. Alright, in prior videos we have talked about what heat and work are, and we've said that those are ways of energy transfer. Right, so now what we're going to do is define a thermodynamic variable, which is the internal energy, that will allow us to do the bookkeeping of the energy in a particular system. Right, so by tracking changes to the internal energy, we'll be able to know if that system is gaining energy or is losing energy as a consequence of a process. Right, so the internal energy, we're going to be using the letter E to denote it, and some other books prefer to use the letter U, and that's something that you have to be on the lookout for. Right, the way to define the internal energy of a system would be to simply add all of the potential energies and all of the kinetic energies of every single particle in the system, and that sum will tell you what the total internal energy is. Of course, for a molecular system that is exceedingly difficult to do, because in a molecular system you're going to have lots of molecules, and then you will have to think about all of the attractions or repulsions between all of the electrons of the system, the protons in the system. Then if those particles are moving, then you will have to consider that as well, and of course that's very difficult to do. Fortunately for us, it turns out that in chemistry we're not interested in the absolute total internal energy of a system. We're only interested in changes to the internal energy whenever a chemical reaction takes place, or whenever you have a gas expansion or a gas compression, right? We're only interested in the changes in a particular process that is of interest to us. So we're not interested in this E. Instead, what we can do very well is track changes to E. We can calculate this change to the internal energy. All right, so it turns out that, well, because there's only two ways for energy to flow in and out of a system, to be transferred in and out of a system, then the change to the internal energy in any system has to be the sum of those two unique ways to transfer energy in and out of a system. Right, so this is our first law of thermodynamics, which again tells you that because energy can only be transferred as either work or heat, then the change in internal energy of a particular system has to be the sum of those. Okay, so that's our first law of thermodynamics. Now let's take a little bit more, talk a little bit more about that internal energy. Internal energy is something that we call an extensive property, and that means that depends on the system size, right? So if you could, for example, think about the total energy of a gas right here at a particular temperature, given number of moles and so forth, or the total energy of a gas which is twice the size. It's pretty obvious that because you have twice as many molecules here as there, then the amount of energy that you will have will be double here than there. Okay, so that is what an extensive property is, a property that depends on the system size. That is not particularly useful in chemistry. We always like to use intensive properties, and those are properties that do not depend on the system size. Right, so to take care of that, what we're actually going to do is generally always work with molar internal energies, which simply have the definition of energy over the number of moles. Okay, so that will be the units of this energy then will be joules per mole, and that will be a quantity that will not depend on the amount of sample that you actually have. All right, so that is the discussion of energy being an extensive property and how do we make it intensive. There's one more thing that we have to talk about in referring to the internal energy, and that is that the internal energy is something that is called a state function. Okay, I'm going to write this down because that is important. State function. A state function is a function that whose changes do not depend on how a process is carried out. Okay, so for example, height will be a state function. If I want to calculate the difference in height between this marker being down there and this marker being down here, the only thing that I need to know is what is the initial height and what is the final height. Okay, the difference between those two will tell me how much the height has changed. Notice that height is a state function because it really does not matter how do I get from the initial point to the final point, right? I can go from the initial point to the final point this way directly, Or I can do this. I can move this marker around, right? The process is now entirely different, but if I end up in the same place and my initial state is the same, then the difference in height, the change in height, is exactly the same. So obviously height is a state function because its changes do not depend on how the process is carried out. It turns out that energy is also a state function, and it really doesn't matter how you do the process. The change to the energy given an initial set of conditions and a final set of conditions that are identical will be exactly the same. Now that is an extremely useful property of energy because we can take a chemical reaction, for example, and it turns out that as long as your initial reagents and final products are the same, it actually really doesn't matter how you carry out the reaction. The difference in energy from reagents to products will be the same. Now that is extremely advantageous in chemistry because, well, suppose that we're interested in biochemistry, chemistry inside our bodies, right? We can think about the complicated chemistry that takes place when glucose is being metabolized in your cells to generate energy. Well, the reaction will be glucose reacting with oxygen, eventually to lead to CO2 and water. Now, the reaction mechanism inside our bodies is extremely complicated. You have to go through high glycolysis, and then you have to end up with oxidative phosphorylation. There's many chemical reactions that are actually coupled together, and it's very difficult to do experiments in a living organism. It will be really difficult to then calculate how much energy is released when you burn glucose with oxygen in your cells. Right? However, because energy is a state function, we can run that reaction in a simpler case. Right? We can actually just burn glucose with oxygen in an open container. Right? And if we're able to measure the difference in energy or the energy released in that much simpler reaction, then because energy is a state function, the energy that we get in the reaction in the simple model, right, just burning it with oxygen in an open atmosphere, and the difference in energy that happens when the reaction is running in our bodies will be exactly the same, which is extremely useful as you can imagine, right? So then energy, the internal energy, is a state function, which is extremely advantageous. Now, something that is very important is that while energy is a state function, work and heat are not state functions, and this will be a source for confusion. Right? It turns out that work and heat actually depend on the way that the system is carried out. So we're going to have to be very careful in defining the conditions in which the process is taking place when we calculate work and heat. Right? So it will be very common to say to write heat not only as heat, but as heat sub B or heat sub P, to say that we're either working at constant volume or at constant pressure. And because the value of Q will change. That's because Q and work are not state functions. Okay, so in this video we have introduced the concept of internal energy. Then we've seen that we're interested in changes to internal energy, and we can calculate those with the first law of thermodynamics. And then we finished by noticing that the energy is a state function, but work and heat are not.